Okay, so I do want to tell you that there are a few things I just want to announce. Um, on the syllabus, you may have noticed that there's something I call a graded problem set, which I have for every chapter. The chapter 1 is sort of almost ready. So you should check Blackboard. Usually I give you about a week to do it. Okay, so we're finishing chapter 1 today. So some of the problems on that are things that essentially we haven't really covered yet, technically. But anyway, so you should check Blackboard on that. We have a quiz on Thursday. I just want to tell you how I go about doing these quizzes. What I do is I wait until the second hour. So sometime around I guess 11 or 11:05, something like that, I'll be giving that quiz out. I'll ask everyone to put their cell phones away. You can only use a calculator, so don't just bring your cell phone to do calculations. I won't let you use it. You have to have a calculator. And the other thing is I ask people to sit every other seat so that so everyone does their own work. I will have two versions of the quiz, but just don't be surprised when I ask you to move so that you're not sitting directly next to anyone. I do that for every class. And let's see. Oh, what is it on? It's on what we did the previous week. Okay. So the more difficult dimensional analysis problems that I'm going to go over now, I'm not going to have anything like that on the quiz. So it's basically the content of the first week of school. So nothing I do today on chapter 2 will be on it. And if I have a dimensional analysis or a conversion problem, it'll be a pretty simple one. Okay, so it's info, or not just info, but what we covered, material from the first week of school. Does anybody have a question about that? Anything? All right, so I'm recording on Zoom again. I've posted the first 2 lectures on YouTube. Have anybody looked at that? A few people. Yeah, if you ever want, they're up there. I have the link on Blackboard. So what I want to do now is to continue with telling you a little more about what dimensional analysis can do for you. I know it sounds like it's a very boring topic, dimensional analysis, but us science people think it's very exciting because the thing about dimensional analysis is you can solve problems without thinking, okay, without having to really do algebra. You could just use the dimensions, use the units to guide you on how to get the answer. So I'm going to give you an example. Let's suppose you want to find the volume of, I don't know, a block of something, some metal. Find the volume of a block that weighs 110.3 grams, okay? And its density is something that you already know. So its density, let's say, is 2.75 grams per cubic centimeter, or as we like to say in chemistry class, grams per milliliter, because a milliliter and a cubic centimeter are the same thing. Okay, so now if I was going, well, one way to solve this problem, you have density equals mass over volume. So it's an equation, a relationship. And one way to solve it is to solve for the volume and then substitute in everything. So if it was me, I would go D times V equals M. What did I just do? What's that called? How about cross multiplying? Yeah, sure, it's rearranging, but I actually, more specifically, I cross multiplied. So then I would divide both sides by the density, and I'd have volume is the mass over the density. Then I would say volume is 110.3 grams divided by 2.75 grams per milliliter. And I would do that division. And what's happening with the units there, I'm dividing by a fraction. So that's multiplying by the inverse of that fraction, the reciprocal. And so I would end up with milliliters. Okay. And the answer would actually be 40.1 milliliters. That seems like a lot of work to me. Okay. And by the way, most students wouldn't do it that way. Most students would do it this way. Or many students anyway, the ones that are not knowledgeable in the methods of dimensional analysis. This is not dimensional analysis. This is the traditional way of solving an equation and plugging in and doing it the hard way. So most students, I think, would do it this. They would say the density, they would use this equation, right? They'd go 2.75 equals 110.3 divided by V. Am I right? Would you do it that way? Who would do it that way? Nobody? Come on. Yes, of course you would do it that way. I've seen this many, many times. And then you would actually solve for V. 2.75 times V is 110. V is 110.3 over 2.75, which is the right answer. But let me tell you, in this step, going from here to here, 30% of students get the wrong answer. Instead of they'll multiply by 2.75 instead of divide. There's all kinds of things that they do wrong in this one step. The correct answer, of course, is still 40.1 milliliters, but there are many mistakes that are made doing it this way. So this is the way that is the best way, according to my experience, my years of experience in this field, and this is a better way. I'm going to just simply say that, and I'm just hoping that I can convince some of you to use this method. This is dimensional analysis. So in dimensional analysis, you'd start with the mass in grams, and then you would put a parentheses, okay? And you would write the density in such a way that the units cancel. Okay, so the density is 2.75 grams per 1 milliliter. And then you see that the grams cancel and you end up with milliliters. And it's a division because the 2.75 is on the bottom. Okay, so I didn't have to think about, do I multiply? Do I divide? It's all done for me if I get the units right. Now, of course, if you write the stuff in the parentheses wrong, if you write it as 2.75 milliliters per 1 gram, then you're going to get the wrong answer. But if you can just keep the things in the parentheses correct by just using them correctly, I mean, it is 2.75 grams per milliliter, not the other way, okay, then you can get these answers with really doing very little thinking. And, you know, if I wrote it wrong and put the 2.75 on top, well, the units wouldn't cancel. And that would tell me that I'm doing it wrong. And I do it wrong, you know, not a lot, but sometimes. And I go, oh, you know, and I just flip it over and I get the right answer. So I just want to encourage you to use this method. And now I'm going to talk a little bit about, and I did this last time, it's very similar to what I said last class, about why does this work? Oh yeah, I forgot. Sorry, I know it's really tough to read. So the reason why this works, why I can just multiply this number by this thing here, is because this thing here is what we call an equivalence relation or an equivalence ratio. And it's because 1 milliliter and 2.75 grams are essentially equivalent things. They both refer to the same amount of stuff. So it's as if you're multiplying by 1, because they really, what's on the top and what's on the bottom are equivalent amounts. And so the only thing that happens here really is you're changing the unit. You know, you're kind of going, it's not really just a unit change because of course you're going from mass to volume, but that's the way this problem treats it. And that's kind of the magic of it. And I hope that I can convince you with these exercises that this is the best way to do this in this course. So that's why. It's because these are equivalent things, and this ratio is sort of like equal to 1. Okay, and so you can always multiply by 1. All right, so let's see. Let's go to activity 8. Oh, so in activity 8A at the top, I'm just going to go over the example that I have there. And so here is another situation where you're asking the question, how many hours does it take for a car to go 162 miles if its speed is 71.0 miles per hour? That makes me think that when I was driving out west this summer, there were lots of speed limits that were 75 miles an hour. When I drove across the country part way when I was a teenager, there were 80-mile-an-hour speed limits. So that was surprising to me, but 71 miles an hour. So, you know, there's a relationship, right, between distance and speed and time, but maybe you don't remember what that relationship is. And you don't need to know that relationship to solve this problem. You simply write 162 miles, and then you use this speed here as an equivalence relation. And you would write 71 miles on the, and you put miles on the bottom because you want miles to cancel, and 1 hour on top. So essentially you're dividing the distance by the speed, because we know distance is speed times time. So distance over speed is time, but you don't need to know this. You just use the units, and you put the unit that you want to get rid of, miles, on the bottom and leave the 1 hour on top, and you get the answer 2.28 hours. Okay. And you don't have to think, do I divide or do I multiply? So it's really much easier. And I really encourage you to do this because there are some complicated problems later in the semester. And if you always solve them the same old way that you used in high school, perhaps, you're going to take a longer time than you really need to solve these problems. So anyway, I'm happy to help you practice with this. If you want to come around, I'm around all afternoon today in building 2. Even after your lab is over, I'll still be there. If you have a 12, is there a lab at 12 to 3? Yes, right. I'll still be there after that. Anyway, so what I want you to do, well, I'll do this problem with you. This is problem 1. So what I give you in this problem is I give you some information. So the information here is that something costs $65 per pound. Okay, so you would write, there's different ways you could write an equivalence relation, $65 1 pound, or you would use it the other way for a problem. I'm not sure which you would use until I see the problem, right? But these are 2 possible equivalence relations that you get from this information. Okay, now the question is how much does it cost to buy 1.2 pounds? So you write down 1.2 pounds, and then you ask yourself, which of these do I use? Which of these is going to cancel pounds and leave me with dollars? The first one or the second one? First one, right? So you put $65 for 1 pound, pounds cancel, and you end up with $78 as the answer to that question, okay? So now I'm going to show you how these problems can get a little bit harder. So suppose you're asked instead, how many euros what it costs to buy 1.2 pounds, but you're not given the number of how many euros it costs per pound. You're only given the amount of dollars per pound. So now you have to do another step. And you could see here that I've got $78. So what I need to do is I could convert that $78 to euros. So this is a situation where you have to look up some information. I'm going to give it to you here. The information is 0.910 euros. I'm just going to call that E equals $1. Okay, so I can write equivalence relation 0.910 euro over $1, or $1 0.910 euro. And which one am I going to use here? The first one, that's right, because it puts dollars on the bottom. I'm just going to write it $1 like that. And so basically I'm multiplying 78 by 0.910 and I get 71 euros. But I want to show you that if you want to attack this question all at once, it's not hard to do. Let me show you how you do that. So if you did this all at once, so in other words, pretend that you haven't done this first step already, you would start with the 1.2 pounds. You would say, okay, I want to get rid of pounds. So I'll put 1 pound on the bottom, $65 on the top. And if I did my multiplication now, I would have dollars, excuse me. But I don't want dollars, I want euros. So I'm going to keep going. I'm going to put $1 on the bottom. That's this one, 0.910 euros on the top. And so then I have to do 1.2 times 65 times 0.910, and I can do that all at once. And I get, of course, the same answer. So either way, you know, but it's a good idea to start getting used to this sort of thing. And so I have two problems here I'd like you to do. Okay, here I'm giving you the information, 42.0 miles per gallon. So what I would like you to first do is write the equivalence ratios, the two different ratios that you could get out of that. And then the first problem, how many gallons for the car to go this many miles? So start with that many miles and figure out which of those ratios you need. For some of you, this is really easy, but I know for some of you, it's not so easy. So I'd like you to work on it. And here we have a second problem added on, just like I did for the first example. So I'd like you to work on 2 and 3 while you're here in class right now, okay? And if you have some questions, maybe you could flag me down. And if you're in the middle, maybe you could come out to the end and ask me a question, because I have trouble getting in there. Well, let's do it Dave and I can cross. Depends, right? Watch it. $58. Yeah, he's actually absolutely right. If you did this problem a different day than I did, or maybe you use a different bank, you know, they fluctuate. So Just make sure you know you're on the right track. So I wrote the answers down. I want you to make sure you get those answers. And the second one is, yeah.
Yeah, yeah, yeah.
I have to tell you that I actually used the wrong conversion here slightly to get this number, unfortunately. Because I used 3.785. Oh, no, that's right, actually.
So I just want to tell you, in case you haven't managed to look it up, that the information that you need is 3.785 liters is 1 gallon. And here you need 1 tablespoon is 14.787 milliliters. Nope. If you needed that on an exam or quiz, I would. I really only expect you to know the centi, milli, kilo. And mega. On the first quiz, I'm actually going to give you that. Okay.
Yeah. Yeah.
I just, yeah. So, I think. Like, a little bit slowly. How are you? If you're talking and you don't know what to do next, go on to 8B. Those are hard to. And for 8B, number 3 and the challenge problem
Are special problems that are due Thursday. 8B, number 3, and the challenge. So I'm going to put the right answers down in here. Yes. Maybe you have a little round off error there. Did you? So yeah, I mean, I wouldn't mark that wrong, but. Oh, no, that is wrong, right? Because you should keep the three sig figs there. So if you told me the answer was 0.41, I would say that's incorrect sig figs. It's 0.412, right? Because there are 3 significant. Yeah. So then you do have some round off error in the final answer. Yeah. So are you working on the second problem? Maybe some of you have even done it. What are the 2 equivalence relations here? What goes on top in one of them? 1 ml and the bottom? Or of course you could flip it and do it the other way. And if you start with 540 grams, oops. By the way, notice that 540 dot, there's a decimal point in that number. So that 0 at the end, is it significant? Yes. Question? That's the next step of this problem. Right, so of course we want to put grams on the bottom, and it's 13.6 grams per milliliter. And that's how we end up with 39.7. I saw a lot of people had this number as I walked around the classroom, right? So you could start with that number. And now the information that I ask you to look up here is basically the information that relates milliliters to tablespoons. And I have that down here. 1 tablespoon is 14.787 milliliters. And so this is a division, basically. .68 tablespoons. But I could have done this all in one step by starting with the 540 grams. 1 milliliter, 13.6 grams. I'd see my grams cancel. And now 1 tablespoon is 14.787 milliliters. Milliliters will cancel. So if you're careful with what you put on top and what you put on the bottom, now, then you can get the right answer. Let me finish my sentence. But this is a division where you divide by 2 things. And now the answer is, again, 2.68 tablespoons. Now, some of you won't get that answer. I'm going to ask if anybody in the room, you don't have to tell me, if anybody instead got 587 for their answer here. Yeah, if you did that, then what you did on your calculator was you put in 540 divided by 13.6 times 14.787. That's what you put in your calculator. So what is your calculator going to do by the order of operations of math? It's going to take 540 and divide it by 13.6. And it's going to take that result and multiply it by 14.787. But 14.787 is in the denominator and you have to divide by it. So what's one thing you can do to solve that problem? .540 divided by parentheses. You could put a parentheses in there. Okay. Or I like to do it this way. This is my preferred method. Because you're really dividing by both of those things in the denominator. Yeah.
So I got 0.69 on mine.
Oh, yeah. Oh, okay.
That's what I found out.
Oh, okay. What did it come out to? With,
Like 5.
let me see. 2.685. Well, that's what I got too. So yeah, that's fine. That's probably the right answer.
Oh, okay, because I thought you said that. Okay, I thought you said 1 ml was equal to 7. Okay,
No,
all right,
no.
that's what I. so
Oh,
I didn't
that's
do-
why
I
you
didn't
got
do
the
that.
wrong.
It's- Yeah. it's because
Yeah.
I thought you said it
Okay,
was
well, I'm
order.
sure somebody else did it that other way. So when you're dividing by 2 numbers in the denominator, you have to make sure you're dividing by both. Anybody else have a question about this? So let's move on to this. These are a little harder. So, and some of you have been working on this already, but this is just to show you that you can do harder problems and you don't have to do that much thinking about the process. This tells you that you're starting with 100 and so here we have how many liters of gas is needed for a car to travel 134 kilometers. So you start with the 134 kilometers and somehow I have to get to liters of gas. So I look over here and I look at my data here, it's my information really. And so which of these will I first use? I mean, there's only one of them that has kilometers in it, right? And so what do I put on the top here? What's an equivalence relation? What are the equivalence relations that I get from this? That's one, this is the other one. So which one of these could I use here to get rid of kilometers? The second one. Okay, so my kilometers go. Now I have miles. Well, there's only one relation here that even has miles in it. Well, there's two different ones that you could use, but only one of them is right. 42 miles for 1 gallon, or 1 gallon, 42 miles. Which one is going to get me to cancel miles? The second one. So now, each one of these steps, if I multiply over here, after the first step, I will have the number of miles traveled. If I multiply after the second step, I will have the number of gallons of gas used. But I don't want gallons, I want liters. So I can write equivalence relations for this one as well. Where am I going to put it? Over here. So 3.875 liters is 1 gallon. I think it actually is 3.785, but I'm just going to go with what's written there. Or I could put a gallon on top. And that's which one am I going to use here? I want to get rid of gallons. So do I use the first one or the second one? Yeah, so I'll put 3.875. It's really 785. I'm sorry. I typed it wrong. That's all right. We're just going to go with this. Okay. And it comes out to 7.7 liters. Because what you're doing now is you're taking 134 and you're multiplying by 3.875 and you're dividing by these two numbers. And that's the answer. Okay. So I'd like you to work on number 2. And as I said, you could certainly do number 3. And then this challenge problem actually is no harder than any of the others. So I'm going to give you a few minutes to work on these. And you'll have to finish them at home, okay? Don't forget, unit power.
If you did activity 5, number 6, I assigned as a special problem. Scan that in on front.
What's your, oh.
That's too bad. Yeah. I'm literally like waiting, but I have to wait. This student's already.
All right. So I have to move on to chapter 2, but I will tell you how to do number 2. So the big thing in number 2 is that, you use the 1 meter is 100 centimeters, but you have to cube the unit. So you're really going to have to multiply by 100 3 times, or use your y to the x key that way, if you know how to do that. And then that will allow you to cancel your cubic meters, and you'll end up with cubic centimeters. So this is really cubic centimeters now. Make sense? So now I want to get rid of cubic centimeters. Well, here's cubic centimeters. And you have to realize that 8.98 grams per cubic centimeters means 8.98 grams for 1 cubic centimeter. So you would write it 1 cubic centimeter on the bottom, 8.98 grams on the top, and your cubic centimeters will now cancel, and you're left with grams. And now we have 454. See, I almost wrote it on top. Did you see that? I almost wrote don't write that, 454 grams. And I said, oh, no, that's not going to cancel my units. I do that all the time. You don't need to solve the what?
Yeah, we don't actually need the.
You need to put the 100 in 3 times on your calculator, or else put 100 cubed in. You can't just put 100 in. This is what. Right, well, you don't need to do it now. You could do it all at the end. That's what I'm saying.
Yeah, like.
I really understand your question. So centimeters cubes cancels. The numbers don't, you have to put the 100 times 100 times 100.
Where
Oh,
At the end, I'll show you.
okay, I see.
So let me just finish this, and then I'll show you how you would actually put it in your calculator. So first you make sure your units all cancel. Now you say, okay, what do I actually put in my calculator? Everything on the top is multiplied, everything on the bottom is divided, and that's it. Or, you don't have to key it in that way. You could key in 100, y to the x 3, 100 cube. I don't know, however you do it on your calculator, or 100 caret 3, there's different ways. And the answer to that is $191. It's 3 sig figs. Okay. By the way, this problem, when I wrote it, this one here, that's a really fast swimmer. That's close to the world record time. I didn't realize that when I wrote the problem, but that's the case. All right, so I hope that you have some time to practice these conversions, especially if you feel that you're not very confident in them. I'm going to be around in my office after class today. I know some of you have lab, but I'll be there even after your lab is over for a while. And also, if I have some people, would anyone maybe want to come around tomorrow afternoon? I would be able to be there if after 2 o'clock or so. I don't know. email me, chances are I'll be there, but if you email me, I'll definitely be there. You know what I'm saying? Building 2 is not that far. We have a nice conference room. Bring a sweater. It's really cold in there. And you could come and practice some of these if you're having difficulty with them. Okay, so I'm going to go on to chapter 2 now. And chapter 2, I'm going to switch back to black, is atoms, molecules, and ions. So there's a lot in this chapter, and I'm sure a lot of it is new to some of you, okay? So, we've talked about atoms. We know that that atoms, we know this today, that atoms are the smallest units of an element. Is this always true though? Right, sometimes we have molecules, like for example, for a diatomic, these are the exceptions, are like the diatomic molecules, like Cl2, where you have 2 Cl atoms bonded together. So it's the smallest unit of an element that isn't a diatomic or something like that. So most elements, so let's just put most elements, because there are elements that have 2 atoms bonded together, and even for the case of sulfur, 8. So, but this is the simplest version of things, okay? We know that atoms combine to form what we call molecules, and that molecules, these are the smallest units of compounds. Well, at least that's for molecular compounds. There's another kind of compound that's ionic, that's different. So the thing is that we know this today. I would say that most everyone in the room knows that today. But back in the 1700s, this really wasn't known. But they did have these 2 laws, one of which I talked about in the first chapter. So before the 1700s, these things were not known. But they did have results of experiments that led to 2 very important laws. These were known. And one was the law of conservation of mass. Now, this is not something you have to copy down, because I gave this to you on a sheet. Yes? Is that what you needed? Okay. So the law of conservation of mass says that matter is neither created nor destroyed, which means that the mass before a reaction is equal to the mass after. They found this from countless experiments, okay? So that was very well known at the time. But the law of definite proportions, which we studied in an earlier class, which was found in 1797, so that was also known before the 1800s, that all samples of a given compound and have the same proportions by mass of their constituent elements. So when we studied this in class, one way I said, we concluded that there was the same mass ratio of elements in a given compound. And as an example, for water, we know that from the activity 2, this was activity 2 from chapter 1, that if you took the mass of O and divided by the mass of hydrogen, you always got 8. Okay, if you did it the other way, you got 0.125. So this was activity 2 from chapter 1. So you always had the same mass ratio. So that was well known at the by the 1800s. So the thing is, what kind of a theory would explain these laws? Because any good theory, so a good theory of the atom, has to explain observations, and observations are summarized in laws. So a good theory of the atom has to explain these two laws. So, okay, so if you were a scientist back at the time, you might have said to yourself, okay, let's think, let's suppose that each element is made up of particles. And let's call these particles atoms, okay? And then let's suppose that all atoms of the same element have the same mass, and that mass is unique to that element. So far we have that matter is composed of atoms, or the elements are composed of particles known as atoms. All atoms of the same element have the same mass. And now let's make a supposition about what happens when atoms combine to form molecules. So let's suppose that when they do that, they always, to form a given compound, they always combine in the same ratio of atoms. So in other words, they always combine with the same number of each type of atom. So when they combine to form molecules, they always combine with the same number of each type of atom. So in other words, that they have the same ratio of atoms. So what would this be for water? So what would the ratio of atoms be in water? Yeah, you would have 2 hydrogens to 1 oxygen in water. So for example, water, you would have 2 hydrogen atoms to 1 oxygen atom, always. Okay? So if this is your theory, very basic, but if this is your theory, then since you have the same atom ratio in every compound, and since specific atoms have specific masses, you're going to have a specific mass ratio. Okay? So this would lead to, okay, so since you have the same atom ratios, we say ratio in a given compound, and since atoms of the same type have the same mass, it means you have the same atom ratio, the same mass ratio. Well, that explains the law of definite proportions, right? Because that's what the law of definite proportions says. So this explains the law of definite proportions, which is a great start for any theory of the atom. Okay, but let's say another thing. And let's say this about chemical reactions, because of course, anything that is going to give you anything in chemistry, we are all about chemical reactions. So let's say also as part of the theory that chemical reactions just rearrange atoms, all right? Chemical reactions rearrange atoms. So if that's the case, then they're just rearranging. That means that you don't add any or subtract any, right? So you have the same number of each type of atom on the reactant side as on the product side. So how does that explain the law of conservation of mass? Anybody? Yeah. There's no loss of atoms, but what else do you know about atoms? They always have the same mass as that whole type of atom. So you have the same number of each type of atom on each side, and each atom has a specific unique mass, and they're all the same for that element. So you have the same mass on each side. Okay, same number of each type on each side, and elements, atoms of any given element have the same mass. So that implies, that's what that means, this symbol, you have the same mass on each side. And so that explains conservation of mass. So that's doing pretty good if you could explain both laws with a given theory. So this is the atomic theory. This is called Dalton's atomic theory. Dalton, this theory was put forward in 1808. And here is just really a list of some of those things that I was just talking about. Matter is composed of tiny particles. They're called atoms. An atom is the smallest unit of an element. An element consists of only one type of atom, and it has a mass that's specific or characteristic to that element. I would say unique. And it's the same for all atoms of the element. This is a statement that I really didn't say anything about, but it is part of the atomic theory that atoms differ of one element, different properties from other atoms of other elements. And here I have said this, a compound consists of atoms of two or more elements combined. And I didn't say this, but generally small whole number ratio. In other words, 2 hydrogens to 1 oxygen. Now, of course, back then they didn't have gigantic molecules like DNA and things like that, where it's not so much small. We have big polymers that are plastics that have enormous numbers of atoms, and you could have a ratio of 187 to 525 atoms of something else in the compound. But, you know, in general chemistry, this is largely true. We deal with relatively small molecules, and they have small ratios of whole numbers, like carbon dioxide would be 1 carbon atom to 2 oxygen atoms, for example, small whole number ratios of atoms. And in a given compound, the number of atoms in each of its elements is present in the same ratio. So obviously you can't have a sample of water where there's 3 hydrogens and 1 oxygen. That's not water anymore. In fact, I don't think it exists. And here in a chemical reaction, atoms are neither created nor destroyed, but they are simply rearranged. And so they yield substances that are different from those present beforehand. So chemical reactions only involve these rearrangements of atoms. So this is a good theory because it explained both of those laws, the law of definite proportions and the law of conservation of mass. And that's what a good theory does. It explains observations. Now, you have to realize, of course, that as science progresses, things can be discovered that would contradict a previous theory. And then the scientist has to go back to the drawing board and come up with some, modification of that theory or something, or maybe a brand new one. Yes. Yeah. That's right. So the question is about that. Well, I don't know what your question is. Was that your question? She was asking whether balancing has to do with this business of having the same number of atoms on each side. Yes. reactions?
Yeah.
Oh, we do. Whenever we want to use them to actually do anything, to figure out how much mass of something you end up with, you know, how much mass of carbon dioxide you get from combusting a gallon of gasoline, you have to use a balanced equation.
Oh.
Yes, yeah. Absolutely. Okay, so that's what a good theory does, and you have to modify your theory if it doesn't work. So we have this great theory. This is Dalton's atomic theory, and that's great. But really, this theory doesn't give you much information about, you know, what is an atom. This theory is kind of, you know, it's great for what it does, but, you know, there's always another question to ask. What is an atom? Okay, what's in an atom? Okay, so in 1909, when this theory was put forward, there had been a few discoveries. Wait, 1809, sorry. No, sorry, okay. 1809 was Dalton's theory. Okay, by 1909, now this is 100 years after Dalton put forward this theory. 100 years later, there was some acquired knowledge about certain things. Okay, so by 100 years after Dalton, electrons had been discovered. And scientists, oh, and actually what's known at that point about electrons was the charge of an electron and the mass of an electron. Okay, these things were known by that time. But there were lots of things that weren't known yet. This is my hardest thing. It just doesn't want to listen to me sometimes. Okay. So what scientists believed at that time were that atoms consist of positive and negative charged spaces, places in the atom where there was positive charge and there was negative charge. So I'm going to call them spaces. They thought that the negative charge was from electrons, but they had no idea about the positive charge. And they really had no idea how the mass and the charge, positive and negative, was distributed in an atom. In other words, they really had no idea of the structure. Okay. So they came up with many different models, many different early models of the atom. And I don't want to tell you about too many of them. I'm just going to focus on the one that's the most commonly known one and the one that was most predominant at that time. And this was a model put forward by this guy, J.J. Thomson. And the model is affectionately called the plum pudding model, which may be more meaningful to people in the United Kingdom, where they eat a lot of this sort of thing. But in USA, we don't really do plum pudding, okay? So I'm just going to tell you what a plum pudding is, so you can have it at Christmas dinner, if you like. Although I prefer my pumpkin cheesecake. What? Yes. Sorry, what are you saying? Oh, yeah, it didn't come out very good. You know what? The copy I thought I printed, it looked terrible anyway, so just, oh, this is terrible. It doesn't have a whole page. Oh, well, it's gonna be too bad. Well, try drawing it, just a circle. And the next one is the one that's gonna drive you crazy. I'm sorry. But I think you could handle drawing that one. I don't know, I'm wondering what happened, like maybe every other page is missing something. I hope not. Yeah, because the next one is gonna be a harder one to draw, but that's all right, we'll just do that.
On Blackboard.
Yeah, well, I hope so. Well, this will be on Blackboard too. This will be in notes. Anyway, just draw a big circle. And so the plum pudding model here. So what is a plum pudding? Okay. A plum pudding is one of these British desserts where it's kind of like a steamed cake. And this is kind of the cake part, the blue part. And the negative charges are like the fruits that are sort of suspended. Those are the negatives, okay? But this cake, in this model, this part here, the whole circular part or spherical part here, this is sort of a spread out positive charge, okay? So that this model showed, what was believed at the time by many people was that the positive charge was spread out in the entire volume like the steamed cake part of the pudding. Pudding is just dessert, really. But it's a cake, like I said. And these fruits were like the negative charges. These are electrons that were suspended in this pudding, like raisins or plums in a one of these cakes. Okay, so the features here was that the positive charge was spread out evenly, and the negatives were negative charges were suspended like raisins in a like raisins in a cake. Okay. All right. So there wasn't a real winner on, scientists weren't convinced about a particular structure of the atom until this one famous experiment was done. And you don't have this picture, so I'm going to try drawing it for you so that you could follow me and draw it with me. So it's called the Rutherford Gold Foil Experiment. And it starts with a source here. Oh, you have that? What the heck? But these copies don't have it, though. It's not the same because it's not in here. Some of them might not have
It looks like.
it. All right, let's draw it, okay? So in this experiment, this Rutherford Gold Foil Experiment, okay, first of all, let me say a few words about this before I try drawing it. So I'm going to get some extra space here. Okay. Okay, so this experiment is gold foil experiment, really changed the idea of the structure of the atom. You couldn't believe it was Thomson's model after you see the results of this experiment. Now, Rutherford did experiments with something we now call, well, they called them back then too, experimented with alpha particles. And alpha particles are produced by radioactive decay, as you may have heard, may have heard that somewhere. My pen is not writing, but I'm waiting. Now, they didn't exactly know what alpha particles were, so it is unknown what they were exactly, these alpha particles. But what they did know, that they were positively charged and pretty heavy, that they had a pretty big mass, okay? Much heavier than an electron. Okay, and that it had a +2 positive charge. So twice as positive as the electron was negative. Okay, and what they did was they took a beam of these alpha particles and they focused them, they accelerated them basically into a piece of very thin gold foil. And they looked to see what happened to that stream of alpha particles after they went through this gold foil. So the reason they were doing this was to find out information about the structure of the atoms in the gold foil. So they were really investigating the structure of the atoms in the gold foil. Now, how did they investigate this? They took this beam of alpha particles, shined it through this gold foil, and they looked to see how the path was disturbed. In other words, did they go straight through? Did they deflect a little bit when they hit the gold foil? Did they go backwards the way they came? So they looked for any deflections in this beam of alpha particles. So I'm going to try to draw a very simple diagram of this. So we have this source of alpha particles, which was actually a very tiny amount of a radioactive substance. I think they used radium. And that gave rise to these alpha particles. Then they had this apparatus, kind of like a circle like that. They had an opening for the particles to get through. So the particles went this way. And they had a piece of the gold foil in here, which is perpendicular, right? So the beam is coming this way, and the gold foil is here. Okay. And then they looked to see what happened to the beam. Did it continue straight? Did it get deflected at this angle or this angle? What did it do? Okay. And so what they measured was the angle here. So they may call that the scattering angle. And that's what they were measuring. So the fact that you don't have this diagram isn't so big a deal. My picture might be a little prettier than yours on when I flip to it, but that's what they were basically measuring. And the question is, what did they expect? And I don't know if you have this picture either, because I think it's on that. Yes, I don't have that either. So here's a picture of the diagram, a little prettier. So they were looking to see these angles here. What were the angles that the beam was scattered? And by the way, this was a luminescent screen. That was how they detected the scattered particles. But this was the picture that we're missing. So you can just draw a circle with your electrons suspended here, like plums in a pudding, okay? And what they expected, if this was the model of the atom, if this was true, if this was correct, and this is what most people thought at the time, then when the beam came through, it might have slight deflections from these electrons, okay? But let me first say that how can you change the path of heavy, positively charged particles? It doesn't have to be heavier, but what has to happen is that beam would have to hit something, actually the same charge, because then it would be repelled. Like to really deflect, it would hit something, it would have to hit something that, well, but we're talking about electric stuff, not magnetic stuff here. But what would have to happen, so in order to deflect this, you'd have to, so in order to deflect the beam, it would have to hit something also positively charged, because that's repulsion. And also very heavy. Okay. But the model at the time was that the positive charge is spread out, right? Remember, the positive charge in this model was thought to be spread out. So it wouldn't actually hit something that was massive that had a large positive charge in this model. So what they expected was that mostly the alpha particles would just simply sail through with very little or no deflection. Okay, and this is showing very little. You can see that if it ran into a negative charge, maybe it would attract a little bit, but these negative charges were only one charge each, right? So they wouldn't be that much in terms of attraction, and they were all over the place. So it might deflect a little one way, then deflect a little the other way. Unless this thing hits a massive positive charge, it's not going to change its path very much. Okay, so what they expected was that most of these would just sail through without much deflection. Okay, so what actually happened was that, so I'm going to draw this part of the diagram again. So indeed, most of the particles did go sail through or had small angles, right? Small angle deflection as expected. But once in a while, they would see something like that. Rarely, but they were there. So this red was very rare, but it happened. In fact, I have a special problem that I posted on Blackboard about Rutherford scattering. That's what this is called. This is Rutherford scattering. Actually, I think it says Rutherford's Gold Foil Experiment. I have a special problem. And it's basically, it's a reading of somebody's summary of this experiment. And actually what they did in this was they actually gave a graduate student the job of looking here for these large angle deflections just to teach him how to use the instrument. They didn't think he was going to actually see anything. So it was absolutely shocking to Rutherford when they saw some of these large angle deflections. Okay, so the fact that this actually happened was shocking, even though it was rare. So mostly all the stuff was over here, but rarely they saw it over here, and it was completely shocking. I can't erase it. It's not going away. All right. So in fact, there was a quote. Here's this. It was as if you shot a 15-inch shell, 15-inch shell into tissue paper, and it came back and hit you. That's how shocked they were. So, you know, we scientists, we kind of have a thing where, you know, you're going along and you're doing your experiments and you're getting it's leading to a certain set of results. You think that you really understand what's going on. And then we always say, oh, and then I did one too many experiments and it totally contradicted what you thought you knew. Of course, it's not too many. We joke and say one too many experiments, but you better do that. It's a good thing you did that experiment, or you might have reported something that really wasn't true. So they did one too many experiments and they actually came up with a very different idea. So the thing is, you have to think about, how do you explain this result? Why is it that sometimes that beam comes back and hits you and you know, at very large angles? And so this led to an entirely new model of the atom. This led to what we call the planetary model. or the nuclear model of the atom, okay? And what this model has in it is that there is a very tiny nucleus with most of the mass and all of the positive charge, okay? And that the electron or electrons orbit the nucleus, and that the size of the atom is much larger, way larger than the size of the nucleus. And so this next thing here kind of shows you the size of the nucleus relative to the size of the atom. I guess I don't have that. I don't even know if you have this one. Do you have this one? Well, you can draw it, or you can wait and print it from. That was a real stupid thing, but anyway. So you could see here that a typical atom would have maybe be 10 to the minus 10th meters in diameter, but the nucleus is 5 orders of magnitude smaller. So if I want to compare this to something in modern day life, I might say, what if you had a football field, which isn't circular, but whatever, and I took and put a tiny, like a little aspirin in the middle of it. Okay, that's kind of like, yes. So how does this explain the results? Okay, so I think you have this diagram next. This is over there. So if you take a look at that diagram, it shows you an atom. So this is like this whole thing is the atom. Okay, and this is the nucleus right here. That most of the time, the beam of alpha particles would not come near the nucleus. Why? Because the nucleus is so small. So it would be very rare that it would actually hit the nucleus. But if the alpha particle did hit the nucleus, you would need a direct hit, right, of the nucleus to get that, what we call backscattering, that scattering at large angles. Well, the nucleus was there. We just didn't know about it. Yeah, so before the Rutherford experiment, you know, I'm sure some people might have thought about it, but no, this was really a very telling experiment. It really pointed them in the direction of the planetary model. So you need a direct hit of the nucleus to get the scattering at the large angles. And this happened very rarely, simply because the nucleus is so small relative to the size of the atom. So that gave rise to the nuclear model, where we have this small, positively charged nucleus, nuclear or a planetary model. With orbiting light electrons, which are negatively charged. And that's, and the next diagram just shows another way of looking at that. Yes. Yeah. Yeah, no, I'm not prepared to tell you that today. Yeah, it's a good point. So this is also showing if you have a whole bunch of atoms and you have this beam going through, and this is the gold foil here. These are the atoms in the gold foil. that most of the alpha particles wouldn't hit anywhere near a nucleus. And the ones that backscatter would be very rare, and that would be when you had a direct hit. Okay, so yeah, I'm not really prepared to give you more details than this, but I would say it's soon be known. So in the early 1900s, it was known that the nucleus contained two particles, protons and neutrons. And the neutrons were neutral, they had no charge, hence the name, and the protons were positive. And so that meant that we know that atoms contain these three particles, protons, neutrons, and electrons. But of course, you know now that there has been many more advances, and physicists know that there are many, many more subatomic particles that make up these different things, which is a topic for maybe a particle physics course, which I'm not prepared to teach either. So, so this chart, which is in the book, kind of gives a summary of properties of these different particles. It gives the location where they are located in the, you have this, right? Located in the atom. And I just, so the location, you can see that in the protons and neutrons are in the nucleus. The electron is outside the nucleus. So protons and neutrons, these are my abbreviations, P for proton, N for neutron. Inside nucleus, electrons outside the nucleus. And we can also look and think about the charges on these different particles. And you notice, and they knew these numbers back then. This was the charge in coulombs. That unit C is a coulomb. That these are the same value, right? So the same value for protons and electrons, but opposite charge, opposite charges, okay? And you could see that by looking at the sign here, negative and positive. Now, and by the way, we call the charges +1 and -1. We don't talk in coulombs, we talk in these unit charges. And if you look at the mass, let's look at this, because this is what we're familiar with. These are gram units here. You could see that these are light particles, but the electron is way, way, way lighter than the proton and the neutron. So let's talk about the mass here. Okay, so we have that protons and neutrons have approximately the same mass. And that mass is about 1.7 10 decided not to write times 10 to the -24th grams. So these are approximately the same. The differences are really for particle physicists to sort out. We're not that interested in it. To us, these numbers are about the same, and we call that one atomic mass unit. Okay, so that's why here you could see that this is in atomic mass units. And the mass is about 1. So the protons and the neutrons are each 1 atomic mass unit, and the electron mass is very much smaller. It's about 1/1800th of 1 atomic mass unit. So that means that a proton is 1,800 times the mass of an electron, and a neutron, same thing. Okay, so really the mass of an electron essentially does not contribute to the mass of an atom. As far as that atom is concerned, its mass comes from protons and neutrons. So I guess I would say that the electron mass is negligible. compared to the mass of atoms of an atom. There we go. I'm gonna write it that way. Okay. So that's what we have. We have this nucleus that has protons and neutrons, the electrons on the outside, most of the mass is in the nucleus. An atom has a lot of empty space, but the question I'd like to resolve right now is, how is an atom identified with a particular element? So what is it about an atom that tells you that it goes with a particular element, you know? And the thing is, it is the number of protons in the nucleus. That's the answer to the question. And we call that Z. That's called the atomic number. Okay. And when you look on the periodic table, the number you see on your periodic table that I just gave out is the atomic number. They're numbered by atomic number. So it's the number of protons in the nucleus. So if you have a neutral atom, to be neutral, you would have to have the same number of protons and electrons. Okay, so in a neutral atom, the number of electrons is also the atomic number if it's neutral. But what can happen is that ions can form. And when an ion forms, does anyone know what the atom does? So atoms can do what to form ions? Yes? They can gain or lose, yes, electrons to form ions. The thing that never changes is the number of protons in the nucleus. So if you have an ion or an atom, you look for the protons in the nucleus, and that tells you the identity of that atom. Electrons can come and go, right? But protons in the nucleus stay the same. So Z is the number of protons in the nucleus. Okay. Yeah. Just one more statement before I go, and that is something called the mass number. Okay, the mass number is the sum of the number of protons and the number of neutrons. Okay, because protons and neutrons both each weigh 1 atomic mass unit. So if you sum up the protons and the neutrons, that number is called the mass number, and it is essentially the mass of the atom in atomic mass units. So, oh well, I didn't even get to the first handout of the day problem, did I? That's all right. Just keep it. We'll continue on Thursday. No, activity problems are generally ones that I do in class. And if I don't finish them in class, then you do them at home. So for example, activity 1 today, we didn't get to it. So if we had gotten to it and hadn't finished it, I would tell you maybe to finish it at home, but we didn't even get to it. The activities are not collected unless there's special problems or some other, you know, special thing. Yeah. No, I'm not collecting. No, we didn't get to it. No way to Hi, Thursday, if you want to come by this afternoon. I could say that I'll probably be around until 4, maybe 5.
Oh, you're off by a factor of 10. Yeah. You have a special problem. Oh, I'm not plugging that, I didn't get that.
Somebody as well.
You can print another copy. I have the ends too close.
Yeah.
Like in the HRV, we didn't get it. Yeah, right. What is going on? It's such a thing. You can't have it. We're gonna, you know, give me the number and I'll tell you how to address it. No, I can't, I didn't cover that. You know, it's not. Oh, I don't know. Okay, so how do you express that as 1/16? Always one. Well, that's not good enough. That's right. Well, yeah. Thank you. But it's still, you're gonna have to round the 1/16, which means you're gonna have to put that number sign.
Oh, okay, so
Even when you do the problem. you know, correct.
okay, so scientific communication accounts of the ones.
Well, you put 1. Or, that's the reason.
Okay, thank you so much.
Yeah.
Okay,
There's that. Yeah, but it's not due till next time.
okay, that's what I was wondering.
Thank you. Yes, I did. So I recall.
So I wanted to ask, the more I look at this, you don't have to tell me, like, I'll hand it in and then, so I can change it, that's what, you know. But I realized that with this cube, hundreds of hundreds. And then I would have to calculate it that way instead of the way that I did.
You can do that.
I don't, so, and I also don't quite have numbers.
Fix it then.
Okay,
Hand it in next time.
oh, sure.
Oh, not.
I know, but like, I don't.
Well, the dude's right across the street from it. We're near the rec center.
I've never been here the last few days.
So did you come in on Mount Pleasant?
Yeah.
So you come in on Mount Pleasant, the first right-hand turn
Yeah.
is security.
Yeah.
the next right-hand turn is what building 2 is.
Okay,
Actually, to come
How are we gonna go there?
from here, go in that parking lot, in that big parking lot by Rob, it's kind of, it's parking lot B, I think.
okay, but if I go out these doors, it's sort of like, correct, not bad directions, I'll help you guys. Cause I wanted to sit
I think
down,
you should just get on the main drag going back to Mount Pleasant.
okay,
And after you pass the main part of campus, you'll see, there'll be trees on right and left. First left turn is the East Campus. Okay, and actually, there's probably a sign that says buildings 1 through 6,
okay,
or rec center. You follow signs to the rec center.
okay,
But before you get to the rec center, count the small buildings on the left, it's the second one.
okay,
It says Department of Education.
alright. Alright, hopefully I'll find it and see you there.
Look at that, they have these maps published.
Yeah.
Even if you did it, frankly, you did it on, for rec center Rhode Island College on your phone. it would probably be
Yeah, I
great.
think I'll make that.
You could try building 2, Rhode Island College, it might even do that. Google is incredible. Good and bad.
We'll be there shortly, like,
Yeah, very soon. Cause I'm driving, I parked that stuff.